So welcome everybody to the session CC5. It is for first session CC5 this afternoon. The first speaker is David Maibach, and he's speaking about quantum gravity meets cosmology, testing quantum gravity with gravitational waves. Please.
Thank you very much. First of all, let me also thank the organizers for hosting us here in the nice conference and for letting me substitute Lavinia, who unfortunately cannot be here today. But I'm sure if you imagine me a bit shorter and with long curly hair, there's almost no difference, I promise. So on Lavinia's behalf, I want to convince you today that the quantum gravity is actually on the edge of being accessible with gravitational wave astronomy. And the way how I want to convince you is the following, by looking at two distinct probes of gravitational waves. One's the classic waveform picture that you know, like that has been captured by LIGO many times now. So this is what we call the resolved gravitational wave. But then also the stochastic gravitational wave background, which has recently made the news with the release of the pulsar timing array data. Yes, which can basically imagine as like some CMB-like version for gravitational radiation. And I want to do so, I want to check these probes with the following three questions. Namely, first, how do quantum gravity effects manifest in them? Why haven't we seen them yet? And what techniques are we working on and are worked on right now to change that? So that at the end, hopefully you get all the tools and insights that you need in order to constrain your favorite theory of quantum gravity. Now, to the first probe, the resolved gravitational waveform, the basic setup is the following. I mean, I'm sure you all have heard of that. You just have two massive objects that are spiraling. At the beginning with a rather constant frequency, which is called the inspiral phase. And then you turn into a merger phase where these two objects, whatever they are, collide and form a single object. This is the part where we are in the strong field regime, which would be naively most susceptible to quantum effects. The problem is, though, that we cannot really, or by no means we have any analytical tools to test this regime. So here we have to rely on pure numerical relativity for now. And then there's the ring down, which is basically a perturbation of the black hole geometry, which decays via quasi-normal modes. And quasi-normal modes are solutions to the perturbation equation with purely ingoing waves on the horizon and purely outgoing waves at infinity. And what is left at the end of this waveform in our detector is not nothing. So this will be not zero actually, but it will be a permanent displacement of the test masses. This is a purely GR effect, which is called the gravitation wave memory, which has been mentioned in view of this conference already a few times. Now in this picture, how do we add quantum gravity to that? There are many ways to do so, and I will just speak about two selected things here. Namely, first, the simple quantization of the black hole. So to treat it like basically an atom, right? So what we can do, what has been first done by Bekenstein and later by Ashtika and other people also, just to mention a few, is to quantize the area of the black hole with the phenomenological constant alpha, which can change from loop quantum gravity theory to theory, with the Planck length squared. And then if you also add angular momentum, for instance, if you look at Kerr solutions, you will even more get like a split of energy. So it's really basically like an atom model. And what you find is that the mass can take only discrete values. Of course, this also depends very much on this constant and how you choose it. But essentially what you find is a split of energy levels. And with the right phenomenology, you see that these energy levels are actually far apart from each other, so they're not overlapping, and you will find a minimum frequency of absorption of radiation. So for loop quantum gravity, the same, you can basically also model with string theory. An example for that are fuzzballs or microstate geometries, which are basically, I think, rather toy models, and they are solutions to 5 or 6 dimensional supergravity. But they essentially replace the black hole with some compact object, which has a fuzzy surface. And I like to quote this nice paper from Chakraborty recently, which tries to mimic this behavior by basically putting a quantum membrane, so a membrane of quantum degrees of freedom with a Gaussian profile, so to add this fuzziness, around a would-be, or put it where the would-be black hole horizon is. And what you can see and what they found here is that you basically get the same behavior. So you have a reflectivity of this surface of this would-be horizon of this membrane, and this reflectivity is also frequency dependent. So what are the consequences of that then for our waveform that I showed at the beginning? Well, you will have for the ring down, for the quasi-normal modes, for the very last stage of the waveform, you will have some sort of reflective properties. So you will have an echo, okay? Which means that after this waveform has passed, that I just showed you in the first slides, you will expect more echoing signals, but only of the quasi-normal modes to reach your detector eventually. And they will also follow this frequency dependency that your theory predicts. Another thing, which is tidal heating, is basically sourced by the same effect, so also by the discrete absorption. But here we are talking about the in-spiral, so the very first stage of this waveform. And since the black holes will absorb the radiation from each other only for a given frequency, this will have an impact on the orbital motion of the black hole. And just to clarify here, I'm not speaking about Hawking radiation, I'm purely speaking about the gravitational radiation and the quasi-normal modes that are emitted, okay? Now the issue, why we haven't found or haven't seen any evidence yet, is the way and I like to think of it as a primitive way, how we detect these waveforms.
Yes, let's take a 1-minute break.
For sure. Questions so far?
Sorry, could you explain a little bit why you discuss dynamics echoes? What's the simple explanation for that?
So, sorry again, the first part of your question.
Why having discreteness of the spectra leads to echoes? Where
Um,
are they coming from?
So if you imagine the quasi-normal modes as, or you can imagine them, as I mentioned, as solutions of the perturbation which decay exponentially, right? But they will have, the boundary conditions are that they are incoming waves at the horizon and outgoing at the infinity, which will be the quasi-modes which we measure. But the incoming part of these solutions, they can be reflected if the horizon is replaced by something which has a reflective property. So it's basically like as if there would be like some radiation going out of the photon sphere. That's the picture that is sometimes drawn. I don't like it so much, but it is sometimes drawn. And then you can imagine that that these quasi-normal modes will then bounce off the horizon and eventually enter the detector at a later stage. Yes.
So the membrane paradigm is just a rewriting of Einstein gravity. What have you done to quantize it, or added some properties to the membrane?
Basically, instead of having like a classical membrane, you give it some like macroscopic quantum degrees of freedom. And these you can treat as operators in the wave function. So you assign this membrane a wave function, and basically look at treat these fluctuations from the horizon as quantum degrees of freedom. This is how you quantize it. But maybe we can talk about this later in a bit more detail. Yeah. But in case you're interested, yeah. Okay. Yes, so as I said, the problem, or why we haven't yet seen that the quantum effects in waveforms, is that we have a rather primitive way of detecting gravitational waves, which is basically a sort of match filtering. So you can imagine that we pick up the data which looks something like this, and then instead of actually from that resolving a signal, we have to create a lot of patterns. So we have to create, like from us, from the theory side, a lot of would-be waveforms that we think could mesh that, and then we push it on top of this data and see which one is the most likely to fit. This is basically how we detect gravitational waves. And as you can imagine, this introduces a major bias towards the model of the underlying theory, which is very bad. And as if this would not be hard enough already, even constructing these templates that we then push on the data and see which is the most likely to fit is super hard, because these three stages of the waveform, they are produced by different techniques. Here we rely mostly on post-Newtonian approximations. Then we have numerical relativity, and then quasi-normal modes. And pushing them together will introduce inevitably a lot of systematic errors. And there's no technique of doing this in a very rigorous way. That's why we, from ETH Zurich and University Heidelberg, started the GV working group, kicked off by this review that we published, and hopefully this will soon be an extension as a book. And what we've done is to use techniques that were first derived by Ashtika and Streube, and after that by many more, including Wald and Zuppers, which are the so-called balance laws. So these are basically sharp constraints on the waveform, on the gravitation radiation that passes through null infinity, and they are derived based on basically the same cornerstones as celestial holography, if some of you have heard of that, which is we assume asymptotic flatness and GR as a fundamental theory. And these constraints allow us to put in some variables of the waveforms and of the event, which is namely first basically the initial and the final mass and the kick velocity, so the velocity of the remnant black hole object, then the gravitational wave memory effect, so this very much displacement that I mentioned at the beginning, and finally the flux, so the energy flux that is supposed to cross, as it was mentioned also in the earlier talks, supposed to cross null infinity. And these formulas are, as I mentioned, sharp constraints, and they are not perturbatively, they are derived on full general relativity. And what we used in this soon-to-be-appear paper is to apply these in a decomposed way, so we decompose it into spin-weighted spherical harmonics, and really look at the waveforms mode by mode. In this way we are able to point out a lot of systematic effects that have not been studied yet before, and improve the templates which we use to match waveforms significantly. And also, then you can add, of course, quantum effects and other effects which will also be constrained by that. And what we're also trying to do is modifying this very equation towards more generalized theories, right? Our group has a large background on modified gravity and also like generalized gravity theories based on other geometric quantities like torsion and non-metricity. And so at the end, we want to find such constraints for all of the theories, or basically on a Lagrangian level, applicable to a general part. And now, finally, let me stress, before we go to the stochastic rotation wave background, the importance of this venture, namely with LISA, and I'm a bit LISA biased here, so there will be also other instruments, just let me clarify that. But LISA will be able to detect these quasi-normal modes. This we know, this is a fact. And if we have the right templates that are without systematics and that include the echo of the would-be quantum black hole, we are able to see them once LISA delivers us data. So this would be an insight, actually, an actual probe of quantum gravity. Now, switching the probe a bit, I'm sure you heard the news of the data release, the pulsar timing array. They have claimed to find first evidence of the stochastic gravitation wave background. They claim that foremost the signal comes from these galaxy mergers. So we have super massive black hole binaries, which give us some signal in the low frequency regime. And they have claimed to measure that. Don't be fooled by the error bars. Okay, the statistical quantities actually tell you that there is a significant evidence for that. But the point I want to make today is that the stochastic gravitation wave background contains a lot more than just these supermassive black holes. It contains galactic and extragalactic sources, which include this, but not only. But more importantly, and in my opinion, more fundamentally, there are also primordial and cosmological sources. So, for instance, you will have the classic tensor perturbations of inflation, which will be in the stochastic gravitational background. You will have evidence of phase transitions in the early universe, and you will have cosmic defects, just to name just a few. And these will be very interesting because they will give us effectively, they will open a door towards the primordial universe, so pre-CMB, really. And quantum gravity here again comes into play, especially in alternative inflationary scenarios. So what you could do is to look at, for example, new aperiodic scenarios or string gas cosmology. And then you would see that, for instance, this seems to be constant line of the inflationary tensor perturbation will get a blue tilt and will be shifted upwards. So it will be like a straight line pointing upwards, which might be eventually detectable by LISA and other instruments. Or you can imagine that new symmetries and new degrees of freedom, as they will influence the evolution of this tensor perturbation, will lead to a bump and more pronounced signals. I will later show also a very specific example for that. But for now, I have to say I'm very biased because I worked a lot together with my former supervisor Robert Brandenberger. I want to focus on cosmic strings. They can arise as topological defects from phase transitions in the universe or from superstring theory. And the reason why I focus on them and why they are so interesting, in my opinion, is that if you detect them or if you're not, it's basically a win-win situation, right? Because if you detect them, well, then you detect them and you have evidence of either the phase transition in the early universe or you have evidence for superstring theory. But if you don't detect them, you will also be able to say something about the early universe because you say, okay, there is no phase transition at this very energy where my cosmic strings are bound to. Because this argument from Kibble in 73 says that basically there's an inevitable formation of cosmic strings once there is a phase transition with the right properties, of course. That I will not name into detail here. So it's very an interesting study that of these cosmic strings, they will, given that they have formed to one way or another, they will form some sort of scaling solutions. So the quantities like number density and so on scale to the Hubble radius will stay constant in time. So we will also have remanence today of cosmic strings. And they will produce, as I mentioned, quite a large contribution to the stochastic gravitation of background. And they will do so by the decay of string loops. So you can imagine if you have a network of long strings, eventually they will cross, they will intercommute also with themselves, and they can form these string loops, which decay via just the wiggling modes of the string, via kinks and via cusps, which are basically formed due to this intercommutation of two strings. Yes, and they will contribute largely to this signal, as this graph shows here. And it is expected, which is basically more or less a back of an envelope calculation, but it will be expected that LISA, for instance, will be able to constrain them by a large margin. But this here has to be taken with a grain of salt because this was not a proper simulation. It was just like an estimate, let's say, okay, based on an estimate also for the sensitivity of LISA. Now, as I mentioned already, there are multiple origins of cosmic strings. So unfortunately, even if you detect them with the stochastic gravitational wave background, we'll have to include other probes in order to distinguish between origins. So say either it's string theory or it's primordial phase transitions which actually created them. And this is where my former supervisor put a lot of effort in and really promoted this program. Now, the problem, or why we haven't seen some evidence yet, even though the pulsar timing area already claimed to see the stochastic gravitation wave background, is that it's still very faint. So it will be very challenging even for future instruments like LISA. And also, we have the problem that all of these sources that I just showed here, they will basically overlap, right? And this will be like a huge accumulation of gravitational wave signals, like stochastic distributions. So it's really the question, how can we discriminate signals and how can we filter it out? And in Heidelberg, again, we grouped together with people from the LISA cosmology working group to try to resolve this issue. And our technique is based on quite fundamental principles of observer dependence of these signals. Namely, we use kinematic anisotropies that are introduced by the motion of our galaxy. This has also been done for the CMB, for instance, at the very early stages of analysis of the signal. What sounds rather trivial, if you look at just the monopole, dipole, and quadrupole contribution of the galactic motion, is not so at the end, because you have to remember that LISA is an overlap of multiple motions. So we have basically 3 satellites in LISA that orbit around the Earth around the Sun. I don't think I have to mention that. And then we have the galactic motion and also the motion of the individual satellites. So there's a huge mathematical and numerical effort that has to be done to, at the end, extract like a signal in general. Also because LISA is only or mostly sensitive to the normal vector of this plane here, right? So we have to rotate this normal vector basically around 360 degrees to see a signal of the overall sky. And what we were able to show, and what we applied in this paper, is that we managed to extract this cosmological motion and showed that these signals, like these from originating from cosmic strings, for instance, these slope-free signals are actually detectable. So given the noise level of the instrument is in a favorable condition, we can actually see such contributions. And even more important, I think, is that we also applied these techniques to more distinct features, such as primordial black holes, for instance, which can be modeled by some curve like this, where you have some sharp peaks and features. And these boost the signal effectively, so they boost our kinematic anisotropies. And via this way, we are able to actually more confidently distinguish these features in the ensemble of what we call the stochastic gravitational wave background. So at the end, we have very much found evidence that LISA might be able to actually find these characteristic features, and since we applied it only on a very sparse grain of frequency grid, there's the hope of actually measuring piece by piece in the frequency space, and at the end reconstruct these frequency, these shapes, these spectra in frequency dimension, to at the end get